I'm Antoine Tenart. I work at Red Hat as a software engineer. And today we'll be following a packet journey through the networking stack of OpenShift. I'm not an OpenShift expert, but I went to the previous talk about imposter syndrome, so it should be fine. So I'm not going to present like the full picture of how it should be working and going through that. We'll do it the complete opposite way. We'll be sending a packet and looking at what's happening, and then hopefully we'll be able to start explaining a bit what we see and build on top of that and refine what we want to see to get at least part of the picture. So that will be our setup for today. We have an OpenShift single node cluster, and on it we'll have two pods. One will be an HTTP client. The other one will be an HTTP server behind a service. And the idea is to make an HTTP request and to get back a file of 10 kilobytes. So it's a pretty simple example, but it should look like things you could have in production, where you have pods behind services and you have other pods making connections. This is for simplicity reason using a single host. So we have a single node. Thanks to it, we'll be able to see the connection and see the full connection. In real-world environment, you should have many nodes, but at least for what we're concerned about, that should not change much the logic of what we want to see. So we get this. You have two pods, one client, one server. You can look at the IP address of the HTTP server pod, which is this one. So you can try to remember it because we will see it again. And if you want to check it's the same one, and I'm not lying, you can try to learn it. And then we expose the service, which is exposing our HTTP server pod behind another IP address. So the idea is from the client to contact the service IP, and hopefully we'll get a request to the HTTP server one, and hopefully we'll see what's happening. So that's what we will be doing, but then we need to look at what's happening inside the system. And to do this, we'll use a tool which is called Retis. So it's a kind of new tool that was released not so long ago. It is still under development, but it's working fine already. And the idea is to track and trace packets inside the networking stack of Linux. You can think of it as being a TCP dump-like tool, but at the function level. So TCP dump will operate at the device level, but we are operating at the function level. So you should have a lot more granularity. But in addition to that, it will also gather contextual information, whether it's from the data path or the control path, so that you can have a better picture of what's happening. Because it's at the function level, if you probe too many functions, you'll see the same packets multiple times. So an important thing about Retis is also it should be able to track packets so that you can then reconstruct the flow of a packet. You can actually see if a packet is the same one or if it's a different one. That will help things. It also knows quite well about Open vSwitch, which, spoiler alert, will be quite interesting in the next slide. And then last but not least, we have some post-processing abilities. We'll use one which is sorting event, basically putting all packets that are the same together. But you can do many more things, like including we have Python bindings. So everything that you see as event is exported as a Python object, and then you can implement whatever you'd like. So this is a typical Retis use and output. In red here, you have a way to use it. So this is a script we are distributing to use it in the container. It makes it easy to consume. We are collecting data, meaning we want to see event, we want to see packet. And here we are doing a simple thing of filtering ICMP packet. And this is a single Retis event. So you have, at first, in green, generic information, like you have a timestamp. You have a probe, so this is where the packet was seen, and some other things. On line 3 here, in the middle, in purple, you have the packet itself. It really looks like a TCP dump output, so you should be familiar with it. And then in blue and in white, we have this extra information, contextual information we're retrieving. One is about the device, and here in that example, the other one is about a contract. So that is the contract information that is linked to this packet in this probe. And then you have many more events. This is a single one. As you can see, it can be pretty large, so it's not easy to fit multiple events, even a single one sometime on slides. Even the screen is quite big, so I remove many things from the output, from the event, so that you can see only the important part. But of course, if you run it, you will see everything, which is much more interesting to read. Okay, that was introduction. Now what we want to do is to, well, follow an HTTP GET, so that will be a TCP connection. To make things easier, we'll start, and also because it's logical, we'll start by following the first packet, which will be the SYN packet. Okay. So step one, we'll be making our HTTP request from the HTTP client pod. We are using the service name, so that will resolve to the service IP. This is not the pod IP. I should maybe have used a different name. And then on the node itself, we'll run Retis. Here we are collecting data. This if dump is some pre-configured configuration file. We are here interested in packets. So we are enabling something that is called a collector, but the SKB one. So we will be retrieving packets. And then we are filtering on TCP and port 800, which is, at least should be, what we are interested in, because there are like other traffics going on, and well, you don't want to see everything. So if we run this, we will be seeing this kind of output. So we have 4 events. Okay, 1, 2, 3, and 4. And each event has a lot of information attached to it. So if we look at things, you can see here that is a probe name. It's something xmit. This is when a packet is about to leave an interface. That interface is ETH0 here. We have the device information. We also have the network namespace information. So it's basically leaving ETH0 on that network namespace. And if we think about our setup, it's probably leaving ETH0 on our client pod, right? Then we can see another event. It's called something receive something. So that is when a packet will be arriving in an interface. The interface is this one, so it's E4BAA something. And that is a different network namespace. Okay. So it basically crossed network namespaces. Then here we have, again, the xmit. So it's going out of another interface, which is another one here. And you can see the namespace is the same. Okay? And then we have an interface receiving a packet that is ETH0, but it's not the same because it's not the same namespace, right? So this is probably the server pod, right? So basically packets arrive in the server. And in between, I can tell you that this is the host network namespace. So packet went from a pod to the host and then back to a pod. One thing is we have 4 events, but when looking at the packet information, we have the same IP ID, we have the same TCP information. I don't know, but it's probably the same packet, right? Okay, so if we have a look at information about that one, we could do the same with this one, that interface. We can see it's part of the OVS system interface bridge. We don't really know yet, but it's obvious Open vSwitch is probably involved here in doing something. The other thing we see is that interface is a virtual interface, and so it is linked to another virtual interface in another network namespace. So what we see is we have probably two links here between namespaces that allow packets to flow through one namespace to another. OK, so we can start drawing something. It should look like this. We are still missing bits, but we have a pod. We have our interfaces, part of the obvious system one. And the only thing that is changing is, at least in the slide, is the destination IP. It starts by being the one of the service here. And then you can see on the other one, that's another one, another IP address, which is the one of the pod. Okay, so there were some things happening modifying that IP address. Okay, next step. So this is nice. We saw OpenVSwitch is involved, so we'll enable some OpenVSwitch capabilities to get extra information. And also we saw multiple packets that should be related. It looks like to be the same packet. So we'll enable tracking to try to reconstruct the flow. So step 2. We'll be doing the exact same HTTP request, and here we are enabling SKB tracking and OVS, OpenVSwitch. One thing we do is we will store the event into a file, so we can later post-process those events by sorting them and trying to group every packet that is the same together. Okay. So we end up with this. At the beginning, it's exactly what we had before. So you have something going outside of an interface. This is ETH0, then it is received another one. I remove the information, but that is the interface on the host. And we see extra, and we'll see new event related to OpenVSwitch. We'll come back at it later. So with tracking, we could group two events together, so we can see at least those packets are the same. But then we see extra event, even though if you look at the TCP and IP information, it kind of looks like the same packet. So we started to group things, but we can see that in between this event, which is happening inside OpenVSwitch, this is in the kernel, this is also in the kernel, something's happening, and the packet is not exactly, well, from this point of view, at least right now, it's not the same, but it's probably the same. So looking at what's happening in OpenVSwitch, we can see here that we have a miss event. And because of this miss event, we'll have an upcall. So a miss event in OpenVSwitch is when you have a packet that is not matched by any flow that is installed in the kernel. All right? So basically, we don't know exactly what to do at that point, which is why we have to do an upcall, which is sending that packet to user space, because OpenVSwitch has a user space part. And then in user space, it can be matched against the flow, and then the packet can be reinserted. The flow can be also inserted and executed inside the kernel. And then you have like this other event, which is executing another flow. Okay? Because now it's available. So this is exactly what I said. So we can draw a few more things. We have our diagram, and well, in between here, what we see is a miss event. Things are happening in user space, and then both the packet and the flow are being inserted inside the kernel and executed. Okay, but we are still missing things because well, we have a gap here, right? And we probably should not have a gap because it really looks like to be the same packet. So next step, well, it's going to user space. We'll try to track those kind of events. That is called, in Retis, OVS track. So basically, we'll be inserting things, inserting probes in the user space part, and we'll be doing some magical things to try to group packets together and to try to, well, unify, identify those packets when they are being reinserted inside the kernel. And now we get this. So you can see at first that is the initial event we had, like in all the other examples. And we can see other events. So I trimmed down a lot of information, right? You would have multiple lines at each thing. And when you look at the last part of it, well, we can see the packet being exmitted from our virtual interface in the host and received in the server namespace, right? So in the server pod. So we have, it was actually the same packet. And now we have the full view of what's happening, right? So you can see from start to the end. So in fact, what's happening, we can see like the miss event we were seeing, then there's an upcall, we have event in user space, and then flow is being executed in the kernel, and then we have an upcall, event in user space, and then flows are being executed in the kernel, and then we have a miss, an upcall, and so on and so on and so on. So you can start to understand the logic of what's happening for this SYN packet. So again, this is the first packet of the flow, right? This is the SYN packet. We can try to explain just a little bit what's happening. Here we execute a contract action. So it's basically sending the packet to contract to get some extra information. For example, you can get the contract state, which will be useful for matching against flows. And the other one, we are hashing the packet, which will provide us extra information to be able to, again, match against flows. Here we have a contract action, but with a NAT action with a destination IP. And so you can see here that is a destination IP at the packet, inside the packet at that moment. This is the service IP. And this is the pod IP, right? So we have an action in OVS that will basically denat the packet so that it can reach the HTTP server. Here we decrease TTL. That's time to live in IP, so that's, well, obvious, but we need to do it. And then we have here a selection of an outgoing port. So, well, we need to know into what virtual device to put the packet so that it can reach the right port. Okay, and then here we select it, and you can see, well, that was selected, and the packet can arrive at its destination. One thing, so you can see that our configuration here is mapping to something that's happening in OpenShift, right? So we did configure a service. We exposed the pod as a service, and that directly maps to things happening in OVS. So that is the pattern that we are seeing. We just explained it, so I won't go back to it. Yep. And we can draw this diagram now, which is pretty much complete in terms of what we want to see today. This is not the end of the talk, but at least for the first packet. So we can see how it looks like. We have miss event, things go to user space, then packets and flows are being injected, and the flow is being executed, and you can do it again and again until the action is, well, is not requesting another match. So in our case, that was selecting an outgoing port to inject that packet. So that was the first packet, but of course we have many more packets, hopefully. So we'll be doing this again. It's pretty much the same. We are enabling here something new which will enrich Open vSwitch flow. So that will provide us information about the flows themselves. Like you can dump the flow and see exactly what was the definition. That can help well, to understand what's going on. I did not copy and paste things, so trust me, this is what's happening. So for the three-way TCP and check, we're basically seeing the same thing. So we have packets going in, we have miss event, we have upcalls, and flows and packets are being reinserted, and so on and so on. And you can see the same logic for those three first packets. So this is because rules, well, flows will depend on contract state. So those packets do not have the same state, which is why you have to match new flows. So you have the same logic. This, of course, depends a lot on how things are being configured. Well, all of the actors involved in this. And then we'll be seeing this. So this is a subsequent packet that is happening, that we are seeing after the three-way handshake. And then we will see this. So it's quite interesting because you can now see those kind of event, flow hit. So we don't have a miss anymore, which means the packet was matched against the flow that is inserted inside the kernel. It's cached, so we don't have to do the upcall. We don't have to go back to user space, and that will save us a lot of time. So it's quite nice to see. So you have a flow hit. This is the open datapath flow. So this is a flow that is inserted inside the kernel. You can read what's here. So you have matching information, other things, and then you have the action, what to do. So we have the action here, and we can see that this is being executed there. So we don't have any upcall in between. You can see here we have our destination NAT happening. Then we have another flow that is being matched and executed. You can see here one of the actions is to set TTL to 63. This is what's happening, right? So it's going here. And then we have another flow that is being hit, so we still don't have to go through user space. And here the action is to select the output port. So the output port is being selected, and then the packet arrives into the HTTP server port. Okay. So it's nice because we don't have any more upcalls, which is more performant. One small comment about it is those flows can expire, so you might see upcalls even after the start of a connection for many reasons that are not part of this talk. Right? So this is what you can expect now. When the packet is going this way, when you have a hit, well, you just execute the data path flow that is inside the kernel, cached, and then you can continue your way. Okay, so we were speaking a lot about flows. We configured the service, and we have flows in the Open vSwitch user space part, in kernel part. So let's try to draw a picture of what's happening from a high-level point of view to try to link all those concepts. So we have a happy user here. He's configuring things, so using the Kube API. Then that is being translated by OVN Kubernetes into OVN concept, so into the OVN representation. And ultimately, that is basically that ends up being logical flows. Those logical flows will be then sent to the OVS daemon and converted into what we call open flow flows. So when a packet is being upcalled, it will be matched against those flows, and then that is being inserted. When those are being inserted into the kernel, it is called a data path flow. Okay? So the idea here is really to see that you have a clear connection between a configuration and things that are happening for a packet inside the kernel. We have time. I wanted to do the bonus. So this is a full. So I kept one event per packet. Okay, so we don't have like multiple events per packet. And this is a full output of what's happening after the three-way handshake and before closing the connection. Okay. So is there anything not expected here? So we are getting a 10 kilobyte file, but we have. So this is a get request. We have the get request. It's been hacked. And then we have the file transfer. And we see 1, 2, yep, 1, 2, 3, 4 packets. Well, we should see a bit more packets, right? Because that cannot be in that small amount of TCP packets. But Retis is showing that we have GSO enabled. So what's happening for those packets? So in reality, what's happening, I won't dive into details, but you'll have, you can think of it as having multiple packets grouped into a single one that will traverse the stack at once. Okay? So that will improve things because you have to parse it only once, and that can go from one point to another one. The idea about that is just to show you you have some optimization already enabled in the stack to do things in a more performant way. There was a talk about GSO, GRO in OpenStack some talks ago, so if you want to get some more details, you can have a look at that. And then we have a few minutes left. I wanted to show you a network policy. So what we do here is we will be applying a network policy which will allow only DNS and MDNS requests from the client pod. And by doing so, we are denying everything else. So when we will be trying to do our HTTP request, we should be denied, right? So something must happen to be denied. So we run Retis again, and this is what we will be seeing. So this is the first packet. We will have an up call. We have, because of a miss event, some user space event. And then we'll have an action that is being executed. And this time we have an action we didn't see before, which is a drop action. Okay, so we have an action telling to drop that packet. The next event here is an event that is not directly into the OVS subsystem, and it is basically freeing the packet for this reason. So OVS drop explicit because OVS just told the kernel to drop the packet. Okay, so and then subsequent packets because well the client will try to send another packet to see if it's working. Well, we will have the same logic, which is a flow hit, so we won't go to user space, and we will be dropping packets without having to do that up call dance of sending packet to user space and then being reinserted. Okay. And I should be on time, yeah. So conclusion, the idea is to see we are doing networking-related configuration on our cluster on OpenShift. And this is being translated to things that will happen inside the kernel, right? So every configuration will not like be linked to a single thing happening inside the kernel, but you can see a clear link between the two. The other thing we saw was the upcall mechanism. So when a packet does not match any flow in the Open vSwitch part of the kernel, it will have to do an upcall to go to the user space part to match a flow, and then things will be reinserted and injected inside the packet, inside the kernel. And when a flow is there already, well, you don't have to do those little dance, and things will be a little bit more performant. There are a few other actions needed, like the TTL one. Well, it's needed. That is needed whatever the configuration you're doing. If you're taking a packet and you're basically routing it to a pod. And we also saw some interesting optimization, even though it was really not a deep dive into that. And of course, keep in mind, this is really a simple example to understand things. But at the core, the logic will be the same. Like, even if you have multiple nodes, even if you have like more advanced configuration, in the end, it will look like this logic. A last word about Retis. It's nice. Well, I find it nice. It's useful for multiple things, including debugging and testing, but it's also very nice to explore things. Like if you don't know how something is working inside the kernel, and you just want to do it by like running a command and actually seeing what's happening, you can use Retis, and you can, well, see that packet, which functions are being used, what is being done at what point in the kernel, and that can help to, well, learn things. So there's a documentation. Hopefully it's not that bad, and here is the official address of the project. Contribution welcome, comment, bug reports, feature request, anything. Thanks. Any question?
So my question is about what, for Retis to function or to use all these SKB, OVS tracing features, do I require anything special for the OVS or special or up-to-date version of the OVS or debugging symbols of the kernel, or what do I need to make all this happen from the...
That's a very good question, and the only part I'm not working on in Retis is the OVS part. So I don't know everything that is done here in the OVS part of Retis. In terms of requirement, at least from my experience, I just had to install OpenVSwitch like the normal thing, and things were working. So I don't expect much more, but I'm not like 100% sure about it because not really my area.
Hey, what about UDP? How would that work?
What about UDP?
UDP packet.
Logic would be very similar. Like you see an UDP packet with the first one. It should not match a flow installed in the kernel part of OpenVSwitch. So you should have this upcall mechanism. You can have multiple ones because of things. And then if the flow being inserted will match like the next UDP packet coming from that connection, it should hit the flow and it should execute things inside the kernel. So it should be pretty similar.
And my other question is, isn't this adding some latency to the packets? I'm in the business of this RTP.
So using Retis or?
Sorry?
So using Retis or using
OpenShift? No. We are using RTP packets to transport voice.
Yeah.
Isn't how much latency is not Retis, but the whole stack adding to a packet?
So your question is if OpenVSwitch will add latency like those upcall mechanism?
Yes.
I mean, of course, yes. Like you have an upcall packet is being sent to user space, and then it is being reinserted. But as soon as a flow is being cached inside the kernel, I think it should be not that bad. It should be pretty good.
Thank you.
Does any of this work without OpenShift, so in a vanilla Kubernetes cluster, or is Retis just OpenShift, and if you're doing it on another cluster, you just won't see anything?
So the question is if Retis is working outside of OpenShift?
Yes, on a vanilla Kubernetes cluster with some other CNI.
Yeah, it basically runs on any not too old Linux distribution. So you can use plain rail, it works, if you use OVS or not. It's not like dedicated to track things in OpenVSwitch. I don't work for OpenVSwitch, for example, and I'm using Retis to debug like kernel stuff in the networking
part. Hi, thank you for the talk, it was really good. What about 2 nodes? Does the tool work across 2 nodes easily?
So again, this is not my area of expertise, but what's happening, I think, is you have a packet. It will be matched to a flow to send it to another node, and then you have encapsulation. I think usually gNIF should be used, so that will be encapsulated. It will go outside that node, and then it will be received on the other one, and then, well, it will go through also the OVS machinery there. Yeah. So it's pretty much the same in terms of logic, but you have this encapsulation, and it's being sent to another node.
So would I run the tool on both nodes, or?
So you can run the tool on both nodes. At the moment, we don't have a way to merge things. So you can't have a unified vision. Yeah. That might come at some point.
Yeah. Thank
you. Okay.
Any other questions? Yes? No?
We are
Okay.
out of time.
Thank you very much.